Hello and welcome to another topic in chemistry. If you are watching these notes as part of Miss Killinan's Try 3 class, it is Unit 8, Date 1. Go ahead and start setting up your focus notes. It is April 5th, 2021. If you're watching these notes any other time, I welcome you. I'm excited to talk about chemistry with you. The topic today is periodic table trends. And the essential question that we will be answering during this lecture is, what is the explanation for the periodic table trends of atomic size, ionization energy, and electronegativity? So these are three of the big guiding things that help us understand a lot about why do things bond, how do they bond, explaining lots of different chemistry patterns and things that we see. But there are other trends. So depending on if you take other classes or if you're watching this for a different class, just know we're only focusing on those three. All right, go ahead and finish setting up your focus notes. When you're ready, let's get into it. The first thing I want to talk about is just what we think about our modern periodic table. And it was based on the work of a bunch of different people from history. Some of them are some pretty interesting stories about how they got their voices heard or how just things about them. But I'm not going to give you the story. You have to do the periodic table reading. So periodic table of the elements, remember that's what PTOT stands for. So it's in Schoology, put it into Notability, and it basically gives you a little bit of like a chem history lesson about the major players in where did we come up with the modern periodic table, the one you're used to seeing in classrooms and online and that kind of thing. So I want you to know a little bit about the development or the history of the periodic table, and that comes from the reading. So you'll do that at some other point. At this point, we're just going to kind of skip ahead and we're going to say we generally know what the periodic table looks like. We know that it's organized into periods, which are the 7 rows. So periods are the same as rows. So if I'm talking about a periodic trend, I'm talking about something that goes left to right or right to left. So across the periodic table are the periods, and you get different physical and chemical properties. So a lot of times there's a pretty big difference between an element here and an element over here, where you'll have a lot more similarities when things are above or underneath each other. So as you go across the periodic table, you get lots of different chemical and physical properties. Most of the similarities are in ups and downs. So the 7 horizontal rows are referred to as periods. So if I'm talking about a periodic trend, I'm talking from like left to right or right to left. All right. So then there's groups, which are sometimes known as families because there's a lot of relationships within that group. And these are the 18 vertical columns. So you've got the up and down comparison. So if I'm talking about a group trend, we're focusing on up and down. So that is the difference, just making sure we are clear about rows versus columns, groups versus families. There's similar physical and chemical properties within a group. So that is the idea about family, right? So like up and down, there's lots of relationships, things that are similar. So there could be a time where something from like here, like way up here and way down here have a lot more in common than here next to each other, depending on which properties you're looking at. So kind of an interesting thing. So up and down, the reason they're in the same column, the reason a row started over was because there was similar physical and chemical properties. Some special groups of ones that I hope you just kind of are familiar with would be that group 1, other than hydrogen, so starting with lithium down, those are known as the alkali metals. The alkaline earth metals are the next group. So I just want you to be familiar, if you heard that reference somewhere, that you would know that alkaline. And the way I like to help myself remember it is that alkali is 1 and alkaline is 2 more letters. So alkaline is group 2. So these are alkaline earth metals. Group 17 is this one right over here, way to the right, the second to the right, the second to the last column on the right. Those are known as the halogens. And then group 18, remember, are our noble gases. And the reason that they're noble and they don't like to bond with things is because they're special because their outermost S and P sublevels are filled. So remember, S can hold 2 electrons, P can hold 6, so you get 8. So that is where we've gotten that octet rule. So why the noble gases are stable is because they have 8 valence electrons. Why do they have 8 valence electrons? Because their S and their P sublevels are filled. Those would always be valence electrons. All right, go ahead and write a level 1 question about any of those notes so far. Pause the video, go back and look at them, kind of think about it, see if it makes sense. Write a level 1 question. Remember, you've got that guide on Schoology if you need it to write some high quality COSTA questions. Otherwise, it's things like list or define, complete a sentence, something straightforward right from the notes. Take a break, pause the video, write your level 1 question, and then come on back. All right, so continuing on, what I'd like to do is I'd like to make a connection to our last unit on electron configurations and our new unit on the periodic table. So here's your periodic table. So we know that there was that thing called the Aufbau diagram with like arrows, and it was maybe a little bit complicated. It turns out that we can absolutely write the electron configuration of an element just by looking at the periodic table because of when we know some organization about it. So the first thing we would know is that these first two columns, remember, represent the S block. And when I say that S block equals row number, well, the row number has to do with its energy level. So for example, the electron configuration for H would just be 1s1 because it's in the first column of the S block in the first energy level. Where something like helium then, now helium is included in the S block, so I'm going to make sure we realize that. So these two columns plus helium technically should be over here based on the S block, but it's over here because it's a noble gas. But the point is that if you're in the S block, to figure out what energy level you are, you just look at the row number. So the row number is the energy level, and then the S would represent what sublevel you're in, 1, 2. So this would be S1, this would be S2. Okay. The P block, remember, is this block, these 6 columns over on the right side of the periodic table. And again, row number is the same as energy level. So notice that there is no P block in that first level because remember, they're in the first energy level, there's only a 1s. But in the second level, there's a 2s and a 2p. So like, for example, boron, it has 5 electrons. Go back here. I fill the 1s1, 1s2, and then 2s1, 2s2, and then 2p1. So I'm adding on to my electron configuration idea just by looking at the periodic table. All right, the D block, remember, is this big chunk here. And remember, we don't have a D block until the third sublevel. But because the 4s fills before the 3D, your hint is it's row number -1. So if you are right here, this is the 5th row, you're really in the 4D sublevel, right? This would be the 3D sublevel, 5D sublevel, 6D sublevel. So this group on, or this section of the periodic table is known as the D block, and it's row number -1 to find the energy level. So then our last one, so this is tricky. 57, remember, is still right here. That's in the D block. 89 is still in the D block. So starting with 58 and 90, that is the F block, and it's row number -2. So this 58 technically goes right here. It's in row 6. 6 minus 2 would be 4F. And then this is really row 7. This would be 5F. 1, 2, 3, 4, on and on and on. So let me show you how we can use the periodic table to write an electron configuration. I'm going to go high because I can go quickly using this new trick. Let's do tungsten, element number 74. Oh man, if you had to use the Aufbau diagram, that would take so long. Look at what I can do just looking at the periodic table. I'm not saying it to show off. I'm saying it to show you what the periodic table tells us. So 74, I go all the way back to the beginning. So I'm going to fill up this 1s2. And then this would be 2s2, 2p6, 3s2, 3p6, 4s2, and then now I'm at the D block, which is row -1. So after 4s2, I would say 3d10, back to the regular row number is energy level, 4p6, 5s2, and then this would be 4d10. This would be 5p6. This would be 6s2, and then here's where things get kind of exciting. Before I can get to number 74, I have to fill up 57 all the way through 71. So what I would say is I would say 6s2, 4f14, and then I would go back and I would say 5d1, 2, 3, 4. 5d4 would be the last part of my electron configuration. So look what I just did. You're going to be able to do this too. So you can use the periodic table to write the electron configurations. Now, here's why this is more useful than the Aufbau diagram. One, you don't have to worry about drawing all those arrows and organizing it. You can just look at the periodic table. But here's another thing that's cool. I'm going to actually do thorium, number 90. Are you ready? Oh my gosh, I'm going to do so many, but we can do this. Ready? Here we go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and then remember, before I can fill up this D block, I have to fill up this F block. So after 6s2, I would say 4f14, but remember, I'm going all the way to thorium, 90. So 4f14, then back up here to 5d10, 6p6, 7s2, and here's where things get fun. I'm stopping at 90, but before I can get to 90, I have to fill 89, which is technically in the D block. Here's where the off-bow diagram would not be helpful. I wouldn't have been able to predict this. Here's what actually happens. 7s2, 6d1 for element 89, and then 5, that's right. So 7s2, 6d1, 5f1. So kind of a strange thing that happens. The D1 fills before you get to the F block. So before I can move on to the F block, technically I fill up just the D1. The reason I didn't worry about that before was because I filled the D1, all of the F block, and back to D, so I didn't split it apart. So that was the difference. So notice what I just did. So if you stop in the D block, you can just put all the D block together. But if you stop in the F block, you need to have that D1 represented to show you had to fill 57 before you could get to this F block, or you had to fill 89 before you could get to the F block. So that's kind of the idea. So there is a guide on Schoology that I'd like you to put into Notability and take a look at it a little bit to show you how to use the periodic table to write electron configurations, to think about electron configurations. It's kind of a shortcut, but it's more just streamlined. So instead of having to look up or find or write out that off-bow diagram, the periodic table tells us all we need to know about electron configurations. Yay! Okay, and now I want to get into our trends. So now that you've seen the kind of the organization of the periodic table, some connections with electron configurations, which explains the shape of the periodic table, now I want to talk about general trends. So we're going to talk about 3 of them. The general idea is this thing called periodic law, which says when you put the elements in order of increasing atomic number, there is a periodic pattern in their physical and chemical properties. So if you tried to arrange them, remember in the intro video, I showed you all these different kind of creative ways that people have built periodic tables. That's fine, but the only way you're going to see the patterns that we talk about today is if they are in order of atomic number, from 1 all the way to 118 as far as we know, unless we make or discover more elements, we stop at 118. So when you do that, you'll be able to see the patterns we're talking about. That's what the periodic law states. All right, now let's talk about those trends. The first trend that we're going to talk about has to do with size. But it turns out that all of our trends, really, it's about the nucleus. So what I want you to keep in mind is that protons are big compared to electrons. Now, obviously, if you're just talking about them in general, everything in the atom is tiny. But if you're comparing, protons are big compared to electrons. So the periodic table trends often can be explained by the effective power of the positive nucleus pulling on the negative electron cloud. So that's going to be a common trend a lot of times. So how powerful is the positive nucleus to attract the negative electron? So that's the idea. And obviously I'm just being silly with our Wizard of Oz things. But the basic idea is if the power of the nucleus is really powerful, it can pull in the electron cloud, which keeps things from happening, which is related to the trends we're going to talk about. So keep in mind, protons are big, so if your nucleus is powerful, that interacts with those negative electron clouds in an interesting way. Okay, let's get into it for real. So atomic size, sometimes also called atomic radius, same idea. So what we're going to talk about is it depends on something called the shielding effect. Shielding effect is caused by energy levels. So when you have more energy levels between the outer electron cloud and the nucleus, think of every level as a shield that blocks the power of the nucleus. Think of it like if you had a magnet on your refrigerator, just against the refrigerator, it's really well attracted. But if you put one piece of paper under the magnet, it maybe still is okay. But if you put 7 pieces of magnet or pieces of paper underneath the magnet, maybe the magnet wouldn't be able to attract to the refrigerator as much. So that attraction that is being blocked by the paper. That's the same idea as the shielding effect. If there's more levels between the nucleus and the outer electrons, that nucleus can't attract those electrons as well, and that can affect lots of things, especially the size. So the levels of electrons shield the pull of the nucleus to the outer electrons. And then that means the electrons don't feel pulled by the nucleus as much, which means then it's going to be able to spread out more. But when electrons are just being added in the same level, so think about going across the periodic table like in an S sublevel or a P sublevel, you're not adding any energy levels, you're just adding to the same level, but you are also adding protons. So the nucleus is getting much more powerful, but the electrons on the outside are just staying in the same level. So again, that powerful nucleus is getting more and more and more powerful, the same distance, so it can pull on those electrons a lot. So the actual trend looks like this, the group trend. So up and down columns, the group trend is as you increase atomic number. So as you go down the periodic table, the size increases. So as the atomic size increases as you go down a group. Okay. The periodic trends, remember this means left to right or right to left, but across, so horizontal rows, it decreases. So atomic size decreases with an increase in atomic number or decreases generally from left to right. Now, there's going to be a few exceptions depending on where you are, but in general, the elements on the left are bigger than the elements on the right. The elements on the bottom are bigger than the elements on the top. That's the trend, the general idea. Pause the video and see if you can think about why. Why would the elements at the top be smaller than the elements at the bottom? Why would the elements on the left be bigger than the elements on the right? Pause the video, think about that for a little bit. All right, come on back. This is going to be my answer almost every time. It's the effective power of the nucleus. As you go down a group, there's more energy levels. The nucleus pull is blocked, so it can't pull in the electron cloud. So the electron clouds spread. So the size increases as you go down the group. But from left to right, the elements on the right are in the same energy level, but have a much more powerful nucleus. So the nucleus can pull the electron cloud in tighter, making it a little bit smaller. So size decreases from left to right. That is the power of the nucleus, explaining atomic size, atomic radius. All right, go ahead and do a level 2 kind of question and explain, do a sketch. Like, you could do a sketch an element, sketch the size of potassium versus actinium. So then you would have to think about, which would be bigger, which would be smaller, that kind of idea. That'd be an awesome level 2 question, actually. I love it. Okay, come up with your own level 2 question, take a break, think about the notes so far, and then let's keep going when you're ready. The next trend I want to talk about is something called ionization energy. All right, let's break this word down. Okay, so the energy is causing change. Ion is an atom with a charge, and ization means the process. So how much energy does it take for the process of becoming an ion? The energy needed to specifically remove an electron. So if I'm on the outside, how much energy do I need to pull your electrons away from your electron cloud? So think of it this way. If I have a high ionization energy, I'm saying, no, the electrons are all mine. Don't touch them. I'm going to keep them. I'm going to hold them really tight. If I have a low ionization energy, I'm saying, sure, whatever. Take the electrons. You don't need much energy to take my electrons. You can have them. That's the idea. Okay, so let's talk about this. Group trend, meaning up and down. The lower on the periodic table, so increasing atomic number, the ionization energy decreases as you go down a group. So the elements on the bottom of the periodic table, it is easier to take to remove an electron. And then periodic trend, left to right or right to left, it increases with an increase in atomic number. So The energy needed to remove an electron is higher on the right side of the periodic table where the atomic number is higher, so from left to right. So again, the elements on the right side of the periodic table, it takes more energy to remove their electrons. The elements on the bottom of the periodic table, it takes less energy to remove their electrons. All right, once again, pause the video. Actually do this. Take some time to actually think and process. Why would it be easier to take an electron from the elements on the left or the top? Why is it harder to take? I think I just misspoke. Let me repeat what I should have said. Why is it easier to take an electron from the elements on the left and the bottom? Why is it harder to take an electron from the elements on the right and the top? That's what we're talking about. Okay. Why would it be? Pause the video, think about that. Why would that be? All right. Are you noticing a pattern? What am I going to say? It's the power of the nucleus. Okay, so let's talk about it. It's easier to take electrons from the bottom. Why? Well, because they have more shielding, remember? So that shielding blocks the power of the nucleus. So the positive nucleus doesn't attract the negative electron. So it's easier for someone else to remove it because they can't hold on to it as tightly. But then from left to right, on the right side of the periodic table, there's way more protons, remember? So increase atomic number, those nucleus is way more powerful. So those positive nucleus, or the positive nucleus has way more power. So it's holding on to those electrons way more tightly. So it's saying, mine, don't touch. I'm going to hold on to all my electrons. Now, the other thing you might notice is, well, wait a second. The elements on the right are generally negative oxidation number, meaning they are gaining electrons to be stable. Well, that fits this. It's hard to remove their electrons. So, in fact, their powerful nucleus is taking other people's electrons. Versus the ones on the left, those are elements that are more likely to lose electrons, have a positive oxidation number, right? Well, again, that's because their ionization energy is low. It's easy for elements to take their electrons. That's why they have positive oxidation numbers. See how all these things are coming together? Oh, I love this periodic table discussion. There's so many things this connects to that we've learned about before and will keep learning about as we continue this trimester. All right, let's do the last one, electronegativity. All right, so clearly it has something to do with electrons, and electrons are negative. Okay, so what does it mean? It's the tendency or likelihood of an atom to attract electrons to itself in order to bond. That's the idea. Okay, let me show you this. So if this is an element, how strongly can it attract other electrons to itself? So atom's tendency to attract, this is of course being a little silly, like atom, they're personifying an atom. So if it has a high electronegativity, it is very likely that it can attract electrons to itself. If it has a low electronegativity, it's not very likely to pull electrons to itself. Maybe it can share electrons, or it might just let other people take its electrons. That's the idea of electronegativity. Here's a visual. Pretend that this is an atom, okay? So this is the nucleus attracting its own electron. Now imagine this is another atom. This nucleus is trying to attract this electron, but this nucleus is also trying to attract this electron. That would allow it to bond. Okay, but another option is, look, this nucleus is trying to attract this electron, and then they could make a bond. Well, which one? Let's call this element 1 and 2 or element 3 and 2. Which one is more likely to be able to take the electron? Will this nucleus be able to take the electron, or will this nucleus take this electron and create a bond? Can you think of it? Okay, well, the answer is this one is less likely. Why? This nucleus is so far away from this electron, it can barely attract its own electron, let alone take from somewhere else. So because this atom is so big, this likely has a lower electronegativity than atom 1 that we called it. So atom 1 can get close enough and has a nucleus that's strong enough to attract this electron away, and then this would make a compound. They would bond these atoms. So again, it's about the effective power of the positive nucleus. This nucleus is stronger and can get closer. This nucleus is so far away from this electron cloud, its power is less effective. That's a visual of electronegativity. All right, here's another little cartoon version of it. So take a look at this. So here's your nucleus. And it's got, kind of one level of shielding it's showing. Here's your nucleus. Look, it's got two levels of shielding. And so if we're trying to decide if this element will be able to take electrons compared to this element taking electrons, which one do you think will be more likely? Which one has the more powerful, effective nucleus? Yeah, oxygen does. This would have the higher electronegativity. It has less shielding, meaning there's less blocking the power of the nucleus to attract the electrons. So between these two examples, oxygen would have the higher electronegativity value. And look, it's even showing you. This also, because it has less shielding, it has a smaller atomic radius than sulfur does, because again, these electrons aren't being pulled as tightly by this nucleus because of those two levels of shielding between the outer electrons and the nucleus. So, kind of showing some cartoon examples of the stuff we've been talking about. All right, let's go ahead and officially define this. There is an actual electronegativity scale come up with this person called Linus Pauling, and he just pretended that there was numbers. Like he just talked about, like, he goes from 0 to 4 is basically what it is. That's what I mean by arbitrary. Like he could have gone from 0 to 100 or 1 to 10, but he went from 0 to 4. And so basically, if you have a higher Pauling electronegativity number, you are more likely to attract electrons to yourself. And it's based on something called electron affinity, which is basically how much do you like electrons, and ionization potential, how easy is it to make an ion. So it is based on actual chemistry things, but by arbitrary, I mean the numbers 0 to 4, he could have done anything. So the group trend for electronegativity is electronegativity decreases with an increase in atomic number, or as you go down a group. So the bottom elements have a lower tendency to attract electrons to themselves. The group trend then is it increases with an increase in atomic number, or from left to right. So once again, the elements on the right side of the periodic table have a higher tendency to attract electrons to themselves. Okay. Oh, next should have been, why is that? So we've kind of talked through it a little bit. It's about the power of the nucleus, right? So on the bottom, the nucleus is shielded more. It's not as powerful to positive nucleus to attract other negative electrons from some other atom, because it's blocked, right? But on the right side of the periodic table, those elements have a stronger nucleus compared to the ones on the left. They have more protons in their nucleus, so the nucleus is more powerful. It can attract the electrons more likely than the ones on the left. All right. Okay, go ahead and do a level 3 kind of question. Predict what happens if these two elements come near each other. Now that's a little bit more of a lower level 3. You could do argue, defend, like why would we need to know this? Name or predict a situation where knowing one of these trends like atomic size or electronegativity or ionization energy would be useful. Go ahead and take a look at those. Pause the video, write a level 3 question. Come on back when you're ready. All right, so that does bring us to the end of our notes for today. So your to-do list is to go back and finish any Costa questions so that you're actually reading over your notes, processing, do they make any sense? Do a summary for it today. That's another way to process your notes. So you didn't just write down a bunch of stuff and move on, but you're actually thinking about what you wrote down. If you haven't done so already, put the Unit 8 plan from Schoology into Notability so that you know what we're doing. You can look ahead, see what objectives we have to learn. What are we doing each day? When is the quiz? So if you're someone who likes to plan ahead, that unit plan is for you. And then remember that periodic table reading, the one that tells you kind of the history or the kind of the evolution of the periodic table. Put it in a Schoology, from Schoology into Notability, read it, mark the text, and then there's a little summary processing assignment. So don't forget to go back and do that, because that is new information that I did not give you in this lecture. All right, you could start the Unit 8 practice problems, but that's also kind of what I'm going to ask you to do tomorrow. So if you start them now, awesome, you can ask questions tomorrow. Otherwise, you can, doing today's notes and this reading, that is enough for today. Feel free to stop after that. You could also work on any missing work, kind of try to get caught up, ready to move on tomorrow. But tomorrow is a catch up and clarify day. All right. All right, so then thanks so much for your attention today, whoever you are listening to this lecture. And for those of you in my Killing In class trimester 3, I will see you at our next Zoom meeting tomorrow. Thanks for listening. Bye.